Okay, so I think we can start. Welcome everybody to our next CReAM Brownback seminar. Just briefly to the rules, please have your microphone unmuted during the talk. If you want to ask a question, you can interrupt the speaker and can then unmute your microphone yourself. Please keep in mind that the seminar will be recorded. So when you are speaking, you are and asking a question, you are recorded. So in today's seminar, we will have Shuaizhang Feng from the Institute for Economic and Social Research, and he is speaking about peer effects with endogenous group selection. So please, Shuaizhang, it's your floor.
Okay, thank you, Sebastian, and thanks for having me. So this is a joint research with two co-authors, Yuanyuan, Chen, and Chao, both are from Shanghai University of Finance and Economics. So Yuanyuan has been doing research with me on the education of migrant children since more than 10 years ago, and Chao is a econometrician. So if you have any questions regarding econometrics, I will try to pass to her. So the title is Peer Effects with Endogenous Groups Selection, an application to local and migrant children of elementary schools in Shanghai. Let me first try to explain what we are planning to do here in this research. So basically, we are studying the peer effects of elementary school students in China. And the place is Shanghai, and the time is 2012. I will provide more detailed information on the background later. So what the situation we have is that we have two different types of students, local students and migrant students. By migrant, I mean Chinese internal migrants. And another unique feature of this setup is that we have two different types of schools. We have public schools and migrant schools or private schools. The public schools are of higher quality, but they are capacity constrained. So local students always go to public schools, but not the migrant students. So migrant students can go to either public schools or migrant schools. Our objectives are, so first, to understand the peer interactions among the different types of students on the academic outcomes of the students. So those includes four different interactions: local to local, local to migrant, and migrant to local, and migrant to migrant. And based on that, we want to understand the treatment effect of enrolling in public schools for the migrant students when the peer effects are considered. So let me talk briefly about the existing literature. So the literature we come from is this reduced form literature examining how class composition of migrant, in many cases, in many studies, it's the immigrant students on the performance of local students in the same classrooms. So basically, typically you have on the left-hand side, the outcome variables for the local students, like test scores. On the right-hand side, you have the percent of migrant students, okay? And usually, if you find a negative coefficient, you interpret this as migrant peers having negative impact on local students. But in reality, the empirical findings are rather mixed. You do have a lot of negatives, but you also have some positive or some null effects. Okay, I try to explain more a little bit on this and how we differ from this literature. Methodologically, the existing literature, they usually focus on the effect of migrant on local students, as I just explained. So thus, they kind of explored the other peer effects, like how, for example, how migrant would affect local students and how migrants and local students would affect themselves, okay? And also typically those kind of studies rely on within school random variations in classes. in different classes or different cohorts in a school to identify the peer effects. And also, most studies, they focus on peer effects of predetermined characteristics. By predetermined characteristics, I mean percentage of migrant share, for example, and also other X variables, like the family background, previous test scores, things like that. So they do not model contemporaneous peer effect. There are some exceptions. For example, the Fuller's 2013 paper on quantitative economics, which examines contemporaneous peer effect. So contemporaneous peer effects are very important because if you just focus on predetermined characteristics, you miss a lot of time varying interactions among the peers. And lastly, usually those kind of studies, they do not deal with the issue of treatment effect because normally they do not have the problem school selection. So it's, I haven't seen any other studies on the peer effect in education literature that have the same situation as we have, i.e. two different types of schools. Usually, of course, in other countries, you also have, I mean, public schools and private schools, but usually they only focus on one type of school and do not put them together. So therefore, if you don't understand the the school selection process, you cannot answer policy questions such as school desegregation. So what we do here in this paper, what do we do? So we borrow from the social interaction literature and use a model for interactions on the basis of a simultaneous move game under incomplete information, and incorporate it with switch regression and propose a two-step nonlinear least square estimator. So basically, in our model, we have contemporaneous peer effect modeled in a simultaneous move game fashion. And we have also this switch regression part, which takes care of this school selection problem. We apply our model to the uncollected data in Shanghai with students from two types of schools, public schools with both local and migrants, and private schools with only migrants. And we find basically there is significant positive effects from between all types of peers in both public and private schools. By positive effects, I mean your test score is increasing in your peers' test score. Okay, so no matter what the student type is, increase in your peers' performance always good for you. So second, there's no significant difference between local to migrant and migrant to local peer effects. Those cross peer effects are pretty much the same. Third, but there is stronger peer interaction effects within group than between. So the a local student would be more affected by a local peer than by a migrant peer in public schools. Okay. In other studies, like the one I referred before, the Fuller's, who studies blacks, whites and blacks, they also have similar findings using a very different setup. Lastly, we do find significant contribution of peer interactions to the school treatment effect. So part of the school treatment effect is due to peer effects. So when a student moves from a private school, a migrant private school, to a public school, not only you get better teaching, better schools, or maybe teachers, but also you get better peers. We try to quantify that part. So basically our approach is quite general. I think the model can be applied to investigate interactions among group members with endogenous formed social groups. So by endogenous formed social groups, I mean, similar to our situation, the groups are formed before the interactions start, like in our case. So there is a literature on endogenous interactions, like friendship networks. But there, you first have a class, like a group, and then you start to establish friendship relationships, and then you examine the peer effect between friends. This is similar, but kind of different, still different from our situation here. Okay, so let me try to explain a little bit of the background, the education of internal migrants in China, because the Chinese case is very unique. So in China, because of this, internal migration, we now have more than 250 million of migrants, according to the latest mini census, 2015 mini census. So among them, there are about 35 million children. So those are the school-age children, migrant children, we call migrant children, which accounts for 25% or 1/4 of all the children in the cities. Okay, so their education is a big problem for China. And migrant children, they suffer from two disadvantages. The first is like anywhere else. They are typically from families of lower socio-economic status. They are typically from rural areas. So their parents, their parents do not have a very good living conditions, much lower incomes in the cities. But unlike migrants elsewhere in China, because of this hukou system, the migrants do not have local household registration status, which is like internal citywide citizenship. So because of they're pretty much treated as immigrants. They do not have the legal right to enter local public schools. This is very important. The public schools will still enroll some migrants. And actually the central government encouraged local governments to allow the public schools to take those migrant students. But the local governments typically lack the incentive. Okay, so many migrant students, migrant children, they cannot go to public schools. As a result of this, a substantial percentage of migrant students, they go to low quality private schools, or sometimes called migrant schools. Migrant students also have lower test scores compared to local students, especially for those who go to migrant schools. So we have some earlier studies examining those kind of differences between migrants attending private schools and migrants attending public schools. And there is concern by local parents on the presence of migrants in public schools. So initially, in the public schools, the migrant children, they are in segregated classes, and later the government, the Education Bureau did not allow this. So then they have mixed classes. In our sample, you will still see some segregated classes with all migrants in the same classes. So in terms of the school selection problem, first, the root cause is the hukou system, which I'm not going to elaborate more. Those private schools are started by migrants themselves. They were like entrepreneurs. They started those. They see the demand for education by those migrants, and they started those private schools to meet the educational needs of migrant children. But migrant children still prefer public schools, but they cannot get in. Many of them cannot. So some of them enroll in migrant schools. Enrollment in public schools usually depends on family background and local policies. If you are rich, you have connections, then you might get to, or you know the policy. You know the policy is better, then you are more likely to go, to go to the public schools. Otherwise, you go to private schools. To identify peer effects, it requires us to take into account of the school type selection, because public schools enrollments are not random for migrant students, as I explained. I'm not going to talk about the whole literature, but first, we come from the literature of the reduced form type of percentage of migrants on local performance. It's a very large literature. It's a very, very large literature. And also there are similar studies on examining different races, not for migrants, right, but for say blacks, disruptive peers. They are all very similar in terms of methodology. So what we borrow from is this social interaction models. There is not too many empirical studies in this literature. It's mostly econometric modeling and estimation, and usually it's for not test scores, but just issues like cigarette smoking, stuff like that. And usually this literature, the social interaction models, they do not have this sample selection issue here. There's a smaller literature on endogenous social relationships, like the friends stuffs, which does take into consideration of this endogenous formation of peer groups. But as I explained before, the situation is a little bit different from what we are trying to study. Okay, let me get to the model. So we have two types of students, L for local students and M for migrant students. And also two types of schools, P for public schools, which has both local and migrant children, and M for private schools, which only has migrant students. So a group is just a class, the focus of interactions. Students in a class, they interact with each other, and we study their peer effects. If they are in different classes, then we just assume there's no relationships, they're independent. In class G of size NG, we express relations of different types of students as those matrices, NG by NG social matrices. So for example, WMMP is the relationship between two potential migrants in a public school, okay? So the diagonal elements are zeros. It's a normalization because we don't examine this, how you affect yourself. So basically, it's a peer effect. If I do not equals to J, this WMLPIJ is greater than 0 if migrant I and local J are classmates in the public schools. Okay, so if I am migrant, if I is not a migrant or J is not a local student, then this also equals to 0. If they are not in, yeah. So this is for the other matrices are defined similarly. So basically, this is classmates relationship matrices, taking consideration of the different types of students, migrants or locals. Okay, and the model can be very general, but here I just come to the point. We basically normalize this. Divided by NG minus 1, the number of peers, the peer group size. So if, for example, if I and J, for W, M, L, I, J, P, if migrant I and local J are classmates, this would equal to 1 over ng minus 1. Otherwise, it's 0. Okay. The other matrices are similarly defined. Of course, for this WMMM, it's in the relationship between two migrants in migrant schools. So this is much simpler, right? Any questions before I go on? Okay. Okay, so let's assume that the location, migrant location, where they live is a fixed. Okay, a school district would contain one public school, and maybe also a migrant school. Okay, a migrant child thus face a choice of either go to the public school or migrant school, and the local child just go to the public school. So there's no choice to be made for local child. For the migrant child, SIM equals 1 if I goes to a public school. If it goes to 0, it equals 0 if it goes to a private school, okay, a migrant school. So this is the equation that determines the choice of schools, okay? And it depends on observable ZI of the migrants or migrant family, and this epsilon MSI, the disturbance term. And the outcome variable is Y. Here, the test score. So for the migrants, so M stands, the superscript M stands for migrant. For the migrant,
Shuaizhang, can I just ask a question?
Sure.
So a bit earlier, you said that access to public schools is restricted.
Yes.
So that means the choice 1 must be restricted in some way. So I can't choose a public school even if I want in some districts because access is restricted. Because here you make it basically it's an unrestricted choice. Whenever the index is larger than 0, individual will choose a public school. But if access is restricted, this may be a problem, no?
I'm not sure because, yeah, I'm not sure because, so it depends what's in Z, right? What's in ZI. So ZI includes those kind of family background policy variables that would, determine which type of schools you go to. Either it's public school or migrant school. Basically for public schools, basically the public schools, they always accept some migrant students.
Yes, but there may be 10 migrant students where this index is larger than 0, and the public school can only accept 5.
Exactly. Yes.
So then the other 5 don't have a choice; they have to go to a migrant school. So that's not in your model, no?
That's in the model. That's exactly what equation 1 is trying to capture, right? So it depends on your whether. So let's think from the a social planner's point of view, right? I determine whether you go to public school or migrant school depending on your Z, on the migrant, family background and other kind of variables. So Z determines where you go to.
Yes. But
yeah, I don't think it's a problem.
What I mean is, suppose you have 10 migrant families. They are all having a Z, which would push them over the threshold. So they would ideally choose a private school. But the private school in that district can only take 5 more migrant students. So what happens to the other 5 students?
Oh, you mean public school, right? Yeah.
Public school, yes, sure, public school, yeah.
Yes, I understand your question. Yeah, but it's Z is not like a a threshold. Once you reach certain Z, you are eligible to go to public school. Z includes everything that determines the likelihood of you go to public school, right? So it's not like yeah, of course, if the public school don't have enough space, then you can just go to then you have to pretty much go to migrant school. But
okay, so this is a latent index. That's the way we have to think about it. Okay.
Yes, exactly.
Okay.
Yeah,
okay.
exactly. Yeah.
Okay.
So then the people who go to public school will have even higher Z, even better Z. Yeah. Okay. So here, if you go to public school, we observe Y1IM star. If you go to private school, we observe Y0IM star, right? And the treatment effect for migrant I is the difference. Of course, we don't observe both. Okay, so this is the test scores. For migrant I, given SIM equals 1, which means this migrant goes to the public school, right? Your test score equals Y1IM star, which has those basically 4 components. This first part, UG alpha P, is class and school characteristics, okay? And this XI beta P is your own characteristics. And those two, starting from lambdas, are peer effects. So lambda MMP is the marginal effect of the average, basically the average peer effect of migrants. So M means, so this MM means migrant to migrant, okay? And which is the combination of all the migrant peers. Here, WMMP IK is this relationship matrices, okay? And this is the expected value of the peer, migrant peer, okay? And this is similar defined, but for local students. So for this migrant I, it has 2 parts of the peer effects. One from the migrant peers, and the other from the local peers. And this is the error term, okay? Similarly, for local child, J, it also has class and school effect, self own characteristics part, and this peer effect. And again, the peer effect comes from both migrants. The first term is the peer effect from local child J's migrant peers, and the second term is from local peers, and the error term. For the students for migrant I who go to a private school, it's a little bit simpler because you only have one type of peer, the migrant peer, okay? And this is the error term, okay? So here, as you can see, the migrants' outcome, the students' outcome depends on the expectation of their peers, basically. Their expectation of their peers' performance, okay? There's a game theoretical foundation, which I'm not going to talk about. Basically, your utility will decrease if you are different from, very different from your peers. So they want to, conform to what their peers do, but you can have different interpretations.
Can I just ask a question? So if you go back to that slide, so if I look at the first sum in the first expression, how do you deal with class size? So the way this is written is that you basically sum, so suppose WPMM is equal to 1 for, because, so then basically if you have, and you multiplied with the expectations, summed over that is, if you have 5 migrant peers, then the total effect of those 5 migrant peers is 5 times lambda MMP. Is that what it is?
No. So basically here, size doesn't matter. This W is normalized. So W is always divided by NG minus 1, which is the size of the peer. So the class size minus 1, the person.
Okay, so no matter whether there is 1 migrant student or 20 migrant students in that class.
Exactly.
And the relative fraction or relative share of migrant students to local students doesn't matter neither.
The relative share matters, you know, because this W and this W are all divided by NG minus 1. So what matters the relative share. The total size doesn't matter. So
okay.
this WMMIK is divided.
Okay, so the relative share matters, but what doesn't matter is the size
average.
Of okay.
Yes.
Okay.
Yeah, exactly. So basically what matters is the average of your peers' test scores, but we are summing them over, you know, each peer and taking expectation. Yes.
Okay, thanks.
Yeah. Okay, let me explain a little bit more. Those are pretty straightforward. U are class school features. Those are correlated effects. X, I, and Zi are exogenous. Okay, publicly known to all classmates, and epsilon are observables. Here the information set. The I's information set basically is a public information component plus his own unobservable idiosyncratic error term. So you know your epsilon I, but you know other than that, everybody has the same information. Everybody knows everybody's X, and everybody knows how the classes are formed basically. And those are these are the influence from the peers, which are usually called endogenous effects. And lambda MLP measures intensity of the average marginal effects of a local classmates to a migrant student in a class of a public school, okay, with the local characteristic controlled. Those lambdas are similarly explained, as you know, I just explained this. Okay, the basic assumptions. Let me go through this. So first, there's error terms expectation is 0. This is, you know, very typical. And epsilon is IID across migrants. This also simplifies things. And Z and X are exogenous. This last assumption is kind of important. Conditional on school type selection. So once you select a school, the students are assigned to classes exogenously, okay? So the class assignment rule depends only on individual and school characteristics, not on the error terms. Otherwise, we will be in a, in a mess. You know, we need to take care of this class selection problem. Typically in the literature, people assume random selection, random assignment of students into different classes. Okay. So here, notice that we have this peers heterogeneity.
Sorry, can I ask? So that's an assumption, right? So there is no random assignment to classes. That's an assumption.
This is assumption. Yes. Yeah.
Yes. And
what about? We're going to check that. Yes.
What about school assignment?
School assignment. You mean who goes? Which type of schools they go to?
Yes. So the migrants.
That's a selection issue we try to take care of. That's equation 1, basically.
Yeah, but how do you, but how do you identify that? What's your identification here? Is that parametric?
We have an IV. So yeah, you are going a little bit ahead of me. So Zi and Xi must be different. So we have an IV variable, which is the location, which is where the migrant parents lived prior to they go to school. And
okay, so that's your exclusion basically.
Yeah, exactly.
Okay.
Yes.
Okay.
Yeah.
And within every class, I'm sorry, within the 2 classes of schools, do you assume schools are homogeneous? Like, because within public schools, there could be several public schools.
Oh,
right?
exactly. Yeah, it's a very. Yes, it's a very good question. Yeah, the simple answer is yes. In the model, we assume they are basically the same. But in empirical work, we have school fixed effects, which hopefully take care of that. Yeah, we have school fixed effect. Yeah. Okay. Here, let me explain a little bit on the heterogeneity part. So, two agents, two students, I and J, they should have the same expectation on the third person, okay? Because the only information they have is the public information. Like I said, we are assuming that all the students having the public information plus their own epsilons, basically. So the expectation, two different students will have the same expectation of the same student, okay? One student, but the expectation, each person's expectation is different, okay? So for person I and person J, their expectation, like the last part, the person I, yi, other people is, let me say it this way, other people's expectation on person I and person I prime will be different, because the expectation depends not just on the peer effects, but also on the X and the school and classes. Of course, this will be the same if they are in the same classroom, but X will be different. So we have heterogeneity here for the students. Okay, so this is, I think this page is very interesting because it compares our approach with the typical way of doing this in the literature. Which basically uses the percentage of migrants. Yeah, you see many such papers. Okay, so here if we assume pure heterogeneity away, then the expectations are just based on this local or migrant type. So for example, we use LM to denote expected value of a migrant student's test score. Okay, and then LL is the expected value of a local student test score. Suppose that the expectation only depends on type. Then we can rearrange the outcome equation and get this following equation. And you can see that, if you ignore this ng divided by ng minus 1, this term can be ignored. Then you have here, ngm divided by ng is just the percentage of migrant share. Okay, the percentage of migrant share in the class. And then you can see if you do a regression here, what you get, the coefficient is here. Okay, is this combination. Is lambda LM times LM minus lambda LL times LL. So basically, the reduced form estimate doesn't get something very easy to interpret. Okay, this can be divided by two sums of two parts. So first, let's look at part 2 first. It's LM minus LL times lambda LL. So if LM, which is a migrant student, if migrant students have lower test scores than local students, then you would expect this to be negative. As more, as there are more migrant students, then the peer effects would be negative. Okay, but this term is also important. Suppose migrant students affect local students less than local students affect less students. This will also be negative, assuming LM and LL is the same. So let's assume that migrant students and local students have the same test scores, because they are equally good. But because the peer effects are stronger within group, then we would also expect this coefficient to be negative. So at the end of the day, we don't know what exactly this is telling us. Okay, that's the point I want to make. Okay, so let me see how much time I have. Well, only 20 minutes. So I'm going to skip this part. So basically, here we try to take care of this endogeneity problem. The class relationships are endogenous because of this, school selection issue. Okay. Let me skip this. So the way we are dealing with this is actually quite simple. It's basically similar to Hickman's sample selection approach. Okay, let me just go to this identification issue. So here, what is different from traditional Hickman sample selection problem is that we need to take these expectations, right? Once we, the reason we need to take the expectations is because we have expectations on the right-hand side, okay? So we get equations like this, and then we can solve these simultaneous equations, assuming the lambdas, absolute values of lambdas are less than 1. Otherwise, you know, the equations will explode and do these normalizations. Let me see. Yeah, let me talk about the estimation, because then you will understand what we are doing now. So in the first step, you estimate the selection equation.
Sorry, can I just ask if you go back to the previous slide?
Sure.
So is this about efficiency? If you go back to the, so is this about is this kind of like a seemingly unrelated regressions model?
No. This is for those two equations are for different students. So the first equation is for migrants in migrants in public school, and this is for local student in public school. That's why it's different.
Okay, no. So and you impose cost equation restrictions on the lambdas, for instance.
No, the lambdas are different. There are 4 lambdas here.
All right, okay.
There's a typo. I'm sorry.
Oh, I see. Yes.
Lambda LL. This is lambda LL.
Ah, I see. So why do you? So I'm trying to find out why you estimate this simultaneously.
No, you use for efficiency issues.
For efficiency, that's what I wanted to ask. So it's like seemingly unrelated to regression. This is an efficiency issue. Yeah.
Not really. I don't think it's like seemingly unrelated. I think basically you can think of this as GMM, right? GMM, certain parameters are the same, like beta P and beta P, they are the same.
Yes, so you have restrictions across equations on the parameters, which gives you an efficiency gain, but it's not coming. But it's not coming through the error structure like in Schur models, basically.
Yes.
Okay.
Yes.
I understand. Okay. Thank you.
Yes, you are exactly right. Yes.
Okay.
So here, what in reality, what we do is that we first estimate this selection equation. Then you can calculate this inverse Mills ratio. Okay, the selection part, and then you plug this into this conditional moments in equation 6 for each proposed, and then you choose the parameter values that minimize the sum of square moments. You know, the only part of it is complicated when you actually do this, because you need to repeatedly take the expectations. Like here, I'm not the person who did this, so yeah, so I cannot answer very detailed technical questions, but that's the idea. The difference is that you have those expectations which you need to take, and then you need to solve those simultaneous equations, because these expected outcomes appear both on the left-hand side and right-hand side, which makes this complicated. Yeah. Okay, and then because of this IID condition, you have this, consistency and asymptotical normality issues, which are all taken care of by my co-author. Yeah, but the idea, you get the idea. The idea is, is not that complicated. It's just a Hickman type of selection, plus we have the, expectations, basically Y appearing both on the left-hand side and right-hand side, which complicates things a little bit.
Does the fact that you take expectations, does it deal with the reflection problem? Or because I would imagine if I just regressed observed test score of a focal student on observed test score of the peers, there would be a reflection problem.
Yes. Yeah. Yes. That's how we. Yeah. I actually don't know. It seems like magic, right? Once we take expectations, we don't need to worry about this, reflection problem. I know in some work they try to find IVs to break this simultaneity, but here we kind of like solving the the system of equations at the same time.
Because what I'm wondering whether maybe implicitly is using something as an instrument, because the expectation is predicted based on something.
Oh, yeah.
Maybe
it might be. Yeah. It's a good question. I just don't have a good answer. I will discuss with my co-author more. Yeah.
Okay.
So one reason why you need expectations, I think. So this is an old literature about coherency of simultaneous equation systems. So if I respond to you and you respond to me at the same moment, that's incoherent. It doesn't work. So the systems are not solvable. Arthur van Soest and Arie Kaptein and people have worked on that in the 80s. So I think that in such a setting here, if my responses would be directly to your responses at the same time, we would have an incoherent system. Now, if you have expectations on the other hand, on the right-hand side, then you condition on an expectation and not on an action, which solves the incoherency of the system, and then actually it's identified. So I think that may be, and I think this is otherwise incoherent, besides the reflection problem. Anyway,
yeah. Theoretically, I think it makes perfect sense, right? Your expectations, only your expectations matter.
It doesn't have an equilibrium. It doesn't have an equilibrium if you don't take expectations.
Okay, yeah. What I was not quite sure is that, like, Thomas just asked whether this is equals to some kind of IV, which I don't know. I have to understand this deeper. Yeah. Okay. But let me stop here and show you the numbers, right? Yeah. Okay. So let me just go to the summary statistics. We have 3 types of students: public, local, public migrants, private migrants. Where you can see clearly there's a selection pattern that you have to take care of. The migrant students who go to public schools are much better in terms of father's education, mother's education, in terms of family income. And also for public schools, the local students in public schools even better. They have even higher education levels, also in terms of income, okay? In terms of test scores, which is math test scores, you see the average test score for the local students in public schools is 60. Migrant students in public schools is 55. And private school students is 44. So you can see the difference. Of course, some of those are due to the X, but maybe part of this is also due to peer effect. Okay, class assignment. So here, let me just show you the migrant ratio in different classes. So these are 11. So we have 20 schools, 9 private schools, and 11 public schools. So in the 11 public schools, some have, so for example, school 1, they have 3 classes, and the migrant ratio are kind of similar, right? So here we just assume random school class assignment, okay? But for some schools, so take a look at school 6. You have 2 schools with all migrant students, segregated classes, and 1 class with 43% migrants. Okay, here, so we relax a little bit on on random school class assignment. We allow the schools first to determine whether they have segregated class or not, and then conditional on that, randomly assign students. Okay, so the school class assignment is still exogenous. I mean, it doesn't depend on the epsilons. It only depends on your migrant status, whether you are a migrant or not, or not the person itself, whether this school wants to have a segregated class or not. Okay, so conditional on that, random class assignment. That's our assumption. And we do a lot of tests, which I'm not going to talk about that. So basically, we are taking what we are testing is that conditional on this having segregated classrooms, whether student assignment is random or not, and we cannot reject it now. Okay, so we have this, OS regressions on the basically on the individual characteristics and peer characteristics. Okay, whether they are correlated, and we have this Pearson chi-square test of whether the different classes are the ratios are randomly assigned, and also the standard deviations of the between class characteristics, class average characteristics. And we have this resampling test. It's pretty much the same. They're basically doing the same thing. They are testing whether conditional on having segregated classes, whether students are randomly assigned to different classrooms. Okay, and we also test for whether the math teachers are assigned randomly to different classrooms. Overall, we do not find strong patterns. Okay, all those kind of stuffs are very typical in the reduced form literature that I have talked about. Okay, now let's get to the result. I hope I still have time. 7 minutes. Okay, those are the lambdas, estimated lambdas. Our preferred specification is the last column, which controls for selection, which also have school dummies. As just asked, schools can be very different. So we have a school dummy variable. So here you can see, the lambdas are kind of around 0.8. Okay, and we also calculated the coefficient, using the parameters here. What would happen if you just estimate a reduced form regression on percentage of migrant students? Here it's -7, so you do get a minus sign. But what does that mean? Does that mean migrant students are bad students? Not necessarily, right? Here we see that LM is less than LL, so migrant students, they are worse in terms of test scores, but also the peer effects are also different. Okay, that's also part of the reason why this is negative. Let's look at this. Here we have
the interpretation of the magnitudes. Is it like standardized, or is it just in terms of test score points?
The test score points. It's not standardized. Yeah, sorry. Okay, so the peer effect differences. So first of all, we test overall homogeneity, whether those are the same. So we reject them under 4, under the preferred specification. So they're not the same. Now, then we test whether they are stronger within group than between group, and we do find evidence of that. So like here, lambda mm is greater than lambda ml, and we cannot reject this, and we do reject they are equal. Okay, the same for the other way around, and also we test for symmetry, whether local affect migrants the same as migrants affect local, and we cannot reject that. Okay, so this is the main result that we have. We also look at the marginal effects when the characteristics change. So, for example, if migrants students father's education changes from below high school to above high school, then what is the marginal effect? We see that the average direct effect on himself is 3. Okay, so this is also the raw test score. It's 3 points. And then it also have an indirect effect on migrant peers, which is 0.47, and indirect effect on local peers, which is 0.34. For a local student, the average direct effect on himself is 3.2, and then this is indirect effect on migrants and local peers. The same if we change the family's monthly income. Okay, so this basically gives us an idea of the magnitude of the peer effect. Of course, here even for the effect on itself, you also need to take into consideration of the multiply effect, because once you affect your peers, then your peers will affect you, and then this multiply effect will make this number larger than if we don't consider peer effect. Okay? And lastly, we want to do this policy experiment. We want to look at the treatment effect, which is very interesting and which cannot be analyzed if you only have public school samples. Here, let me just show you this. So we are looking at a migrant student who is currently enrolled in public school. Okay, so that's here in his original classroom, and the hypothetical case, counterfactual case, is to move him to a private school. Okay, so here we calculate predicted score, which is 55, which is basically the average right now. But if we move him to a private school, his test score, expect value would be 50. So the total treatment effect is like 5 points, 5 points. Remember, the test score difference is kind of 11 points, I guess. And we want to see the peer influence. Here we also take the difference of these two parts, which is 1.39. So basically, this is the the part of the treatment effect that's due to peer effects. Of course, you might wonder why this number is very large. It's basically because the averages are very different in those two kind of schools. Okay, we are still trying to understand how to break this into different pieces. But for now, I do not have a very good answer of those. Yeah. Basically, lambda is big, 0.8 is very big, which is typical in those kind of social interaction models. So the multiply effect is kind of big, but at least I think those make sense. Okay, so peer effect is non-trivial in terms of this total treatment effect. That's what, yeah. That's basically what we have. That's basically what we have. In the future, we can consider possible extensions, such as allow students to move and select schools. Then it will get more complicated, because then among public schools, you can choose different schools, right? And also another extension is to allow students or parents to take possible peer effects into account when they are making their choices. In our framework, they don't take consideration of who else will enter the same kind of schools. They just choose schools based on Z. In the future, we might be able to do that, but that also will make things quite complicated. Yeah. Yeah, that's all I have. Yeah, thank you very much.
Thank you very much, Shuaizhang. I think we have time for 2 more questions, if there are any in the audience.
Yeah, I was wondering if you could add, if it would make sense to add back in other peer characteristics. So maybe the share of migrants in the classroom, if that would be something you'd be interested in adding to the model on top of the expected performance, for example.
Yes, that's an excellent question. That's what I was thinking about, because as you see, lambda is big, which some kind of, sometimes creates trouble. You get very different equilibriums with small changes. And I suspect the reason is that we are not adding, so in the model, we are not adding other peer characteristics here. So like here, if we have, x minus I bar somewhere here, it might change, the model. Yeah.
And I'm wondering whether those are even implicitly being used as instruments for the peers' test scores, because they're not in the equation directly, but they're probably used to predict the expectation.
The expectations does depend on X. you know, the peer characteristics. Yeah, but
So
I don't know
if you
how.
would put in all peer characteristics into this equation directly, then you wouldn't have anything left for the build the expectation maybe upon. Or
I don't know whether we will have, you know, some kind of problem when we do that, but it's worth trying. Yeah. But because in some other papers, like the quantitative economics papers I refer to, they do have both peer characteristics x minus I bar and also y, peer outcome variables. In that case, they use an IV approach to solve the problem, but still the coefficients on this x minus I bar doesn't make much sense, and they also explained a lot on why, you know, kind of they have over-controlled stuff. Yeah, so it might have problems. Theoretically, you should have both, but empirically, when you have everything, it might have problems. That's my worry. Yeah.
So so this is very interesting. My question is basically, so this is it is kind of a statistical model.
Yes.
So we don't learn much about why actually there are peer effects. What is the mechanism behind it? Is it knowledge spillover? Is it peer pressure? Or is it something else? So what are your views on that? How do you, what's the economics? What's the mechanism? What's the channel behind the effects you're estimating?
Yeah, you are very correct. So far, there's no mechanisms. There's no, no stuff like that. But if you want to do it, I think we can, because we have other measures, other outcome measures. We can kind of, you know, take a look at, you know, what has changed, you know, so for example, do migrants interact more with migrants peers or with local peers? Or we can, you know, use some of the other outcome variables as the y's here and see how it goes, you know. The question is, the short answer is that we don't have that right now, you know, what you have seen. But yeah, we in principle, we can, yeah.
Okay, thanks.
Okay, thank you, Shuaizhang, for this interesting presentation, and thanks everybody for joining us in our CReAM Brownback seminar, and hope to see you again next week.
Okay, thank you. Yeah.